Right.
All right. Guys, I'm assuming you guys see my screen and the font is not too small, but it might get smaller as we proceed. So let me know if you don't see something. Okay, I'll try to explain that. Okay. So first of all, thank you for inviting me to present my work. The topic that I'm presenting today is actually covering 3 papers, so which involves contributions from multiple researchers and especially my advisor, Dr. Sriram Natarajan. But I'll try to acknowledge everyone here. And the contributors are Nikhilesh Prabhakar and Dr. Sriram Natarajan from UT Dallas, Arjun Manoharan and Balaraman Ravindran from IIT Madras, Dr. Eric Blash from the Air Force Research Lab, and Dr. Prasad Taripalli from the Oregon State University. And the work done was with support from DARPA, AFOSR, ARO, NSF, and USDA, and NIFA, and RBCD SAI. So because there are multiple contributors, you see the support is coming from a lot of people, a lot of places. All right. So, but before I begin on the topic, I would like to give a little bit of background on my research and my lab's research focus. Our lab is called Starling, Statistical AI and Relational Learning Group. As you might know, there are 3 key paradigms in AI: logic, that deals with reasoning for relational data; probability, that uses statistical approaches to handle uncertainty; learning, that uses data-driven machine learning approaches to learn model structures and parameters. There's a research area at the intersection of these 3 that's called Statistical Relational AI, STAR AI. And our lab works specifically on advancing approaches and adapting them, advancing approaches in STAR AI and adapting them for various applications. Recently at ICHKAI 2020, there's a paper which talks about parallels between STAR AI and neurosymbolic AI. Neurosymbolic AI is a long-standing research area at the intersection of symbolic reasoning and neural learning. And there are a lot of similarities and common problems between these in these 2 fields. So if you want to have a look, I'll recommend. They also did a tutorial in ICHKAI in the same year. So anyways, our lab focuses on STAR AI and using STAR AI approaches for real world problems. And we specifically work on problems in domains that have structured and relational data. When I say relational data, what I mean is that there are entities or objects in the data, in the domain, and there are multiple relationships between those entities. So they could think of heterogeneous graph. There could be different edges or different relationship between those edges. The number of nodes in the graph could vary, and each graph might have different features. And most importantly, the relational domains violate the standard IID assumption that most of the machine learning approaches use, right? Independent and identically distributed assumption. These entities or objects are not necessarily independent, and it's not ideal to assume that they are identically distributed. Specifically for domains like healthcare, molecular structures, or social networks. We have worked on Parkinson's disease prediction and predicting gestational diabetes in a cohort of pregnant women. And it's important to capture the subpopulation or pattern or the trends. So, a subpopulation may share eating or drinking or sleeping habits. There could be hereditary factors or genetic dispositions and things like that. So it's important to consider the relation within the entities and not just look at every entity individually. We have also looked at, in the molecular structure, we have looked at drug-drug interaction, identifying adverse drug events, because 2 different drugs can interact and have an adverse effect on various biological processes, as well as learning. We have also undertaken the task of learning chemical entities of biological interest as a concept learning task. We look at a lot of social network data sets as well. And and games, which have some form of relational aspect. However, all of this, the systems that we are trying to build have very high stake of the decision that they are making. So we want to we also focus on human allied. We want to learn systems that are human allied. We want to ensure that the system can collaborate, interact, and learn from humans to solve the problem or make decisions. And the system should be able to explain humans as well. So we try not to vectorize or tensorize everything, and we rather prefer to work in the symbolic representation space as much as possible. So the key takeaway is that we work on relational domains that violate IID assumptions, and we try to build systems that are human allied. My research focus is a small contribution within this big goal, and I look at the fundamental question of how to facilitate generalizable, effective, and efficient learning with human guidance. That is, how to use domain-specific knowledge from humans or experts to improve learning systems. For this, I have used human guidance in different forms. It could be monotonicity constraint, that if my blood pressure increases, I have a higher risk of cardiac arrest or something like that. So that's a monotonic influence information or trend in a domain. We have looked at using causal information of the domains. We have looked at using the hierarchy or the composition of the domain. Here I will talk about how to use the influence information of the domain from humans. And we have also looked at how to get natural language guidance from humans in some of our work. Okay, so the work that I present, so now let me, I'll start the work that I'm presenting today. Here I'm presenting how to use domain-specific influence information from humans for effective task-specific abstractions. And you will see that my work is heavily inspired by Star AI, and hence I will cover some of the basics as needed as we go. Any questions? Okay. Okay, so a lot of real-world sequential decision-making problems are inherently relational. Think of iRobot vacuuming the house. It can encounter a different object on different days, and not necessarily those objects are not necessarily independent. Think a robotic arm that is basically collecting all the pink balls from this basket. The number of balls can change, or the color of the balls can change on different days. If we train an agent to collect all the pink balls, say from the set of 10 pink and 10 blue balls, we expect the agent to perform equally well when the number of balls in the basket change. Say next day we have 10 pink and 10 white balls. So we expect the agent to perform equally well. It should be able to collect all the pink balls. Humans are able to generalize across colors and numbers by having an abstract representation in our head. Say, for example, we for the task of collecting pink balls, we might group all the balls in two categories, one with pink color and one with all other colors. So we would be able to generalize, say, from collecting pink balls from pink and white balls to pink and blue balls. Even for a very complex task like driving to an airport, humans can generalize across terrains and geographies, and sometimes across countries. But yeah, there could be some error, but we can still manage. And we do this by detecting compositionality of the domain and identifying task-specific abstract representation. For planning the route, we abstract the local geography to something that may look like the map on the left. We do not plan for every stop sign or every turn. Rather, we plan for which freeway to take, which exit to use, etc. And while executing the plan, we see a totally different representation of the world. Maybe something that you see on the in the picture on the right. But even in this representation, we leverage task-specific abstraction and like state representations. For example, while taking a left turn, we focus on the vehicles that are coming from the opposite direction in the opposite lane. But while exiting a freeway, we don't care about those vehicles. The key point I want to make here is that humans use different level and different kind of abstractions for different tasks. Based on the task, we change the information that we utilize from the observation that we are or the information that we have. There's a solid paper from your lab that talks about importance of doing similar things within AI systems. It is important for AI systems to also look at the abstract representations and compositions. So my problem statement here, which I focus on, is given a relational sequential decision-making domain, how do we learn an agent and efficiently, that is within some reasonable number of time steps? How do we learn an efficient agent that is compositional, that can handle varying number of objects, that can generalize to different tasks? It can support task-specific abstract representations and can handle different modality of the data. Because sometimes we see some of the information we receive is say speech or text, and then sometimes we receive images. So it is important to make informed decisions using multimodal data. For the first requirement for handling compositionality, what we do is we integrate planning and reinforcement learning. And ours is not the first work. There has been a lot of work that have shown that the combination of planning and reinforcement learning works very well and for compositional and domains which have hierarchy, inherent hierarchy. But we do it for the relational domains. So we call the framework that we propose as RePReL, that is integrating relational planning and reinforcement learning. Here, the symbolic planner at the top decomposes the given task into a sequence of high-level sub-goals. And there are various reinforcement learning agents at the bottom that learn how to execute the sub-goals or achieve those subtasks. In the middle, we have something called abstraction reasoner, and I will talk about it in a minute. But let me just focus on how do we decompose the MDP. So consider the small example. I use this example throughout my slides. So let me just spend a minute. This is an extension of the original taxi domain proposed in RePReL 1999, the MaxQ paper, hierarchical array paper. Here we have a taxi, and it's a grid world with 4 special locations: red, green, blue, and yellow. And there could be multiple passengers. In the original domain, there was only 1 passenger, but in this relational domains, we say that there can be multiple passengers. Different passengers have different pickup locations, and they may or may not have different destination locations. And we have a single taxi in the domain, and the taxi can only be hired by 1 passenger at a time. Okay, so now we are given this domain as a relational MDP, and we use a symbolic planner to first decompose the task. The task here is to transport passenger P1 and P2. So we decompose that task into the sequence. For this case, it is pick up P1, drop P1, pick up P2, drop P2. So we decompose the complete task into 4 different subtasks. And then we learn different RL agents for these subtasks. So for example, we have 2 RL agents here, pick and drop. And pick and drop RL agents are also, the pick agent can say pick up P1 or it can pick up P2. So these RL agents, or the options, as we call it in our paper, these option policies are triggered based on what schematic operator here is obtained by the symbolic planner. So to do this, so what we essentially did here is we decomposed the relational MDP into something called sub-goal RMDP. And in the sub-goal RMDP, we included 2 different, so we modified two components. First is the reward function. Instead of having just the environment reward function, the original reward function from the MDP, what we do is we make the reward function as a combination of a TR and the original reward function. So we add a fixed terminal reward TR when the state reaches the termination state. So if the state if the current state satisfies the termination condition, then it means that it reached the termination state, and then essentially we would have some additional reward here. Otherwise, we would have the same reward. And once the termination state is reached, there is no reward after that. Any transitions after that have no reward, so 0. And we also modified the transition probability function, which is here what we do is we add the 0 probability of moving out of the terminal state. So if an agent reached a terminal state, then the agent has 0 probability of moving to another state, which is not a terminal state. We do this for theoretical purposes, but in practice, as soon as this like a state is reached, which is terminal state, the control is returned to the symbolic planner, and the next RLA or the next option is triggered. So this is just to check everything, check all the optimality requirements. Anyway, so what this RePReL framework provides us, or the combination of symbolic planner and the reinforcement learner provide us, is 2 advantages. One is compositionality, because now we have a symbolic planner that can decompose, the complete task into subtasks. We can get the compositionality of the domain. And now, because we have different RL agents for different subtasks, that is, we have different subgoal RMDPs, we can use task-specific representation in the MDP. So we can define a homomorphic MDP for individual subgoal RMDPs. So that would be the task-specific representation. So let me go back to this example here. So if a human agent was performing the task of picking up P1, she would recognize that the pickup location of P2 is not relevant here. When the agent is just picking up P1, the pickup location of P2 is not relevant. So the navigation or to achieve this task, this information is not relevant. So she would essentially ignore that information and say same thing again. If the agent is dropping passenger P1, then the pickup location of P1 is not required. Only thing that the agent needs to know is that the passenger P1 is in the taxi or not, right? So we can use this relevancy information to reduce or to define a abstract state representation for each subgoal RMDPs. To do that, as I mentioned, we try to use human guidance as much as possible. So to do that, we define a dynamic first-order conditional influence language that provides us this task-specific abstract representation. So first-order conditional influence statements were actually originally proposed in Natarajan et al. 2008 paper. Foci statements is a simple statement of the following format. If some condition is satisfied, this condition is actually a logical formula. If that condition is satisfied, then some set of influence, that is some set of literals, influences a resultant literal. So what foci statements encode is that if the condition is satisfied, then the literal in influence actually influence the literal resultant. We extend foci statements to something called a dynamic foci statement. Instead of using QINF, we use an arrow here, and we have a +1 here indicating the influence to the next time step. If you are familiar with the Bayesian literature, the Bayesian network are extended to dynamic Bayesian network by introducing the time step. So we kind of are inspired by that terms, and we define a dynamic foci statement. So what we are saying here is that the literals in influent set can influence the literal in resultant. It could either be in the same time step, or it could be across a time step. That is, the influent at time t can influence resultant at time t+1. If the influence is on the next time step, then we will have +1 on top of the arrow. If it is in the same time step, we just have an arrow here. So +1 is optional, and like the things that are optional are indicated by the square bracket here. what you see on the left-hand side is our adaptation of the condition that was used in the foci statements. So instead of having a first order or a logical formula, in dynamic foci statements, we introduce the sub-goal. So what we are saying here is that if this task or if this sub-goal is being performed or being achieved, then this literal would influence the other literal. Does it make sense? Any questions?
I have a question.
Yeah.
Can you hear me?
Yeah, I can. Yes.
Okay, yeah. So you're talking about a set of literals, and I'm just curious what those look like. Are they just like, are they booleans? Are they numbers, like variables that represent numbers? What are they?
Yeah, so let me see if I had it in the previous slide. I don't have it. I have an example coming up, so I'll answer that.
Okay.
Any other question?
Yeah, could you elaborate the statement one more time? If condition then influence if result.
Yeah, so what we are saying here is that if a logical formula is satisfied, say for example, if I'm in Dallas, then my time zone that I see is influenced by my current location, or maybe that's not a correct example. Let me see. Okay, let me just give an example for the defoci statement here, right? So if my task is to pick up passenger P1, if my task is to passenger P1, then my reward or my let's say my reward function is only influenced by the current location of the passenger P1. So my reward is 1 or some positive constant when the passenger is in taxi, otherwise it is 0. So that influence information. So defocis don't really tell what is the influence. It just says that a change in the influence would or may not result in a change in the resultant. So there is an influence. What influence is, we don't know. It could be a qualitative, quantitative, whatever influence. We don't know. It's like a influence that is encoded in the edge of a Bayesian network.
What does QIF stand for?
Sorry, I couldn't hear you.
What does QINF stand for?
Oh, qualitative influence.
Oh, I see. Thanks so much.
Okay. Okay, so we think of defoci statements as a dynamic probabilistic logic model. So I'll just make a case of how can we see that, how can we see defoci statement as a dynamic probabilistic logic model here. Think of the space of probabilistic graphical models. We have Bayesian network at the bottom left. In Bayesian network, we have some random variables, and there is some influence between those random variables, right? When we include the time component, we extend the Bayesian networks to dynamic Bayesian network. So that's going, that's in y-axis. My y-axis indicates addition of the time component. In dynamic Bayesian network, we have all those random variables repeated for every time step, right? And there could be influence between those time steps. What SRL models or the first statistical relational AI, star AI models do is they introduce first order representation to BaseNet. So you can think of BaseNet as all the random variables that are grounded. Whereas when we talk about first order, we talk about classes of those random variables. For example, I can talk about Harsha's intelligence influence Harsha's grade here in Bayesian network. But in first order logic, when I talk about a class, I can say students' intelligence influences students' grade. Now, this could be grounded based on the actual students in my domain. I can ground this probabilistic logic model to a Bayesian network. But I would need to know who, like all the students. So probabilistic logic model, they are proposed by different people with different names. They are sometimes called PRMs, probabilistic relational model, Bayesian logic program, logical Bayesian networks, DAPR, things like that. But Luke Derat et al. In 2016, the Star AI book, they show that all of these are equivalent. So it doesn't really matter which one you use. They all can encode the same influence. When we add time to PLMs or time to such first order representation, when we are talking about influences between classes and then add time component to it, that becomes a dynamic PLM. And then in relational reinforcement learning, a lot of people have used dynamic PLMs for factored MDPs. What dephasized statements do are a little bit of extension from the dynamic PLM, because dynamic PLMs only capture the influences. I mean, they capture influences, and dephasized statements actually capture conditional influences. We condition it on the task that is being performed. Does it make sense?
Yeah, I think so.
Okay. So that is why how we look at defasae as some extension of dynamic PLMs. If we have a separate, if we create, a set of defasae statements for each task, then that becomes a dynamic PLM. And then if we ground the dynamic PLM for every time step and every object in the domain, then it becomes a dynamic Bayesian network. Okay. So here is an example of the defasae statements that we used for the taxi domain. If you're familiar with the RL literature, in factored MDP, transitions are shown as a dynamic Bayesian network, something like this. And when we show or capture the MDP as a dynamic Bayesian network, factored MDP as a dynamic Bayesian network, what we do is we add action on the left-hand side and add reward variable on the right-hand side. So we adapt similar syntax. We allow reward on the right-hand side and add action on the left-hand side. So what say for example, my first defasae statement is saying here is that my action and taxi's location influences taxi's location in the next time step, because I have a +1 here. So this is how my influence or my literals look like. I'm not sure who asked that question, but I hope that this example answers that.
So when you say that it influences the next time step, but does it describe the specific?
No.
It doesn't.
No, we don't know the nature of the influence. We just say that change in this at time step t can change value at time step. Can change value of the literal on the right hand side in time step t+1.
So is the assumption that these groupings of defoci statements are complete in the sense that you have all the influence relationships there in front of you, and there's assumed to be not any other influence relationships except the ones in the statements? Yes.
Like a Bayesian network, we assume all the faithfulness assumption. Yes.
Okay.
Yeah. And we have this additional example here, which says that if we are picking up a passenger P, then in taxi P, that is indicating if the passenger is in taxi or not, influences in taxi P at the next time step. But in taxi P, in the current time step, influences the reward of in the same time step. Was there a question?
No, there was just a comment in the chat that was addressing the question that I just asked.
Okay.
But it was just that they're hoping to relax the constraint in the future work where we have a complete. Yeah. And so I still have another question about the primitives here. So
can I know your name? I'm just sorry.
Sorry, yeah. Let me also tilt this down so you can see our bodies.
Okay.
How's that? Much better, right?
Yeah.
I'm Ben, by the way.
I do.
Okay, yeah. So my question is, where did we get these primitives from? Like, did we handcraft these primitives for a specific domain?
Yes. So we do have domain description in the relational format. We are in a setting where we are looking at relational MVPs. So we do assume some form of relational representation. It could be a relational database, or you could have it as predicates. They are all equivalent, or as a graph. All of them are equivalent.
Okay, cool.
Yeah. And we obtain these default statements from humans. So we need some domain. We get this from the domain expert in this work, but we are working on learning these as well. But yeah, all right. So now this slide is a little smaller font. I apologize for that, but I would want to go through this because it's an important process. So given the default size statements, what we want to figure out a abstract state representation. So we have current state S, we have the default size statements, and what we want is a abstract state S hat. The way to obtain the abstract state is by recursively grounding and unrolling the default size statements, the relevant default size statements. I mentioned, okay, so relevant, if my current task is to pick up passenger, then my relevant default size statements are all the default size statements that have pick in the condition, as well as the default size statements that do not have any condition. So these are perpetual influences that always exist regardless of which task you are executing. So these are relevant, and say pickup are also relevant. So for picking up P1, 3A to 3C are the relevant default size statements. So we ground the relevant default size statements starting from the reward, starting from the default size statement that influence reward. So that is this default size statement. We ground it out. We are grounding it based on the current goal that we are forming. So say, for example, in this slide, my grounded option or the grounded sub goal is to pick up P, where my assignment to the P variable is P1. Okay, so I should clarify that the uppercase here means a variable and lowercase means an object or a constant. So I'm trying to pick up passenger P1 here. So I ground my default size statement that influences reward, and I get in taxi P1 on the left hand side, and that any literal that any grounded literal that appears on the left hand side becomes part of my relevant state literal, which is my abstract state. So here in taxi P1 becomes a relevant literal. Then I again ground the default size statement, ground the relevant default size statements for which I have assignments. So for example, I ground what was it? I grounded 3C first, and then because we start with the reward default size statement that influences the reward, and now I'm grounding 3B because now I know the assignment to P variable. I don't know the assignment to X variable, so I can't ground that, but I can ground 3B. So in my depth 2 unrolling, I'm grounding that default size statement, and I receive a bunch of literals on the left hand side. Those again become part of my abstract state, and we can do this recursively and collect all the literals that appear on the left hand side, and this would give me the relevant abstract state. Any questions at this point? Are you able to read this? But
yeah, we can read it.
Okay, great. I did not know how big is this big screen when Saket said you'd be screened on the big screen. Okay, so that is how we obtain the abstract state representation. That is the abstraction reasoner here, which uses the default size statement and current state to generate an abstract state. Okay, so default size statement, sub-goal, and current state to generate an abstract state. Now the RePReL learning algorithm is quite simple, but I like to step through it. Given episode in an environment, or actually we initialize all the buffers first, and then given the current state or the current episode, we send the initial state to the symbolic planner and get a high level plan Then so remember the high level plan is a sequence of sub goals. So for each sub goal, we loop through this these steps that I mentioned now for till either the sub goal is achieved or a fixed number of steps is exceeded. So what we do in the loop is we first get an abstract state. So we have the default statements, we have the sub goals. Now we provide the state to the abstraction reasoner, so we get the abstract state. Based on some current policy, or policy of the reinforcement learner, we figure out what action to use. And then we take that step and we add the observation, the SARS tuple to the buffer, and loop this till we reach either achieve the sub goal or exceed the steps. And then we do this again for every sub goal. And at the end, when we have enough, enough samples in our buffer, we update the sub goal policy using some RL update algorithm. In our experiments, we have used double DQN. We have tried to use PP. We have used PPO. We have used SAT with hindsight experience replay as well. So you can. So the framework is actually quite agnostic to which RL algorithm you use. It should allow batch learning. That's all. Okay. So let me go back to the requirements that I had. So what we covered till now is compositionality. It can handle varying number of objects because it is relational. It can generalize to different tasks. I will show that in the evaluations. It can support task-specific representations, but we also wanted to handle different modalities of data. Our initial RePReL paper was the 2021A paper was actually tabular Q learning. Then we extended to deep Q learning using deep RL agents at the lower level. But then we realized that we also want to allow multiple modalities. That is, we want to allow structured as well as unstructured data. So some of the real world domains that we encountered had, say, raw images or raw text. I call all of that as unstructured data. And structured data could be a graph or a relational database or a predicate representation of the data, something like that. So we have two different modalities of data, structured as well as unstructured. So we added an input preprocessor for the unstructured data. The unstructured part of the observation goes to the input preprocessor. And we extend the default size statements to allow neural predicates, something that was actually introduced in the deep PROBLOG paper cited here in 2018. The neural predicate is just a latent predicate that would be mapped to some embedding, which would be learned by the input preprocessor. So we allow, combination of both structured and unstructured data in the hybrid deep RePReL paper that was accepted in 2022. I have all the references at the end if you want to look at it. So that is what we extended it to. Now I want, any questions before I get into the experiments? Okay. All right, so in our work, we evaluated our proposed approach on different grid world as well as robotic domains. What you see here is the taxi domain, crafts world domain, office domain. It's a relational box world domain. And this is the fetch, pick, and place domain in Mojoko. And we compare RePReL framework with different RL approaches, tabular reinforcement learning, that is tabular Q learning. We also compared it with deep RL approaches, DDQ and PPO SAC. We also compared it with hierarchical RL options framework and as well as the HDQN paper. And a combination of planner and reinforcement learner, that is taskable RL paper, and deep relational RL, that is RL agent, which uses graph neural network based architecture and attention modules to do relational reasoning. So we compare across multiple baselines. What we wanted to aim, let me go back, was sample efficiency, can handle varying number of objects, and can generalize to different tasks. So I'll show results for each of those. There are more results. I can refer you to the paper, but I'll just highlight key results here. So for sample efficiency, I'm showing the taxi domain. On the left-hand side, what you see is the comparison of RePReL with, this is all tabular. On the left-hand side, what you see is a tabular comparison, tabular Q-learning, tabular HRL, tabular taskable RL, and tabular RePReL. So comparison of that, and we see that the number of the number of steps required by RePReL agents in red here is significantly lower than what the other agents require. On the right-hand side, you see comparison of deep RePReL with deep TRL, taskable RL, deep hierarchical RL, that is HDQN, and I say DQN, but it's actually double DQN. So forgive me for that. But we see here the RePReL is in green, and it is significantly lower in the number of samples that is required. So it is sample efficient. Same thing for other office domain here. Again, here on the left-hand side, the chart is for the tabular RL, and the right-hand side chart is for the deep RL. Okay, then we wanted to evaluate for task transfer. I'm showing this on the office domain. What we have here is that, like on the left-hand side, the leftmost is the tabular again. I'm comparing transferred RePReL, which is a solid line, and transferred TRL solid in green, and transferred HRL solid in purple. And the non-transferred or the from scratch learning of RePReL, TRL, and HRL in the dotted lines. And you see that not only the RePReL, like from scratch, it is sample efficient, but even the transferred ones are actually almost zero shot or optimal already in the office world. And this is the experiments. This is okay. This one was tabular, and this is deep learning, deep RL experiments. The task here is to deliver coffee, and the task here is to deliver mail. So you see that it could wait. Oh, there should be one more image here, which then is delivering mail and coffee. I somehow missed it. Okay, so there were 3 images here. Let me see if I can show the transfer here. Okay, so this is the task transfer in Craftsworld domain. We have the task of getting the wood and making an iron in the first plot, and the task is to make sticks. That is getting the wood and then go to workbench to convert woods to sticks. So that is the second task, and we see that the transferred RePReL is actually more efficient than all the previous transferred agents. In the taxi domain, we increase the number of passengers. We transfer the agents and increase the number of passengers, and we see this is deep RL agents, comparison of deep RL agents, and we see that RePReL agent, the green one, is actually able to scale with the number of objects faster. In the relational box world domain, the task in the first one is to just open the lock. So the blue one on the right, blue cell on the right hand side is a lock, and white cell is a gem, and you have to open the lock to get to the gem, and the key color that is indicated in the top left cell. So first task is just to open a lock. Second task is to collect the key. So the key is here. So your first task is to collect the key, then open the lock, and then collect the gem. So the number of objects keep increasing as we go to the right. Here now we have to first collect a key, open a lock, then collect the other key, then open the lock, and then get to the gem. So we see that RePReL agent is able to keep up with the increased number of objects, but TRL agent is not, and Q-learning did not even do it. Okay, and the last domain that I am trying to show here is the Mojoko robotics fetch, pick, and place domain, where we had to stack X number of blocks in a tower, and we trained RePReL and the state-of-the-art relational neural network. That was the paper by Lee et al. In IROS or ICRA, I'm not sure. So they proposed a graph neural network based architecture with I think 2 graph attention modules and graph pooling layers to learn the block stacking in the Mojoko simulator. We see that when we are learning the agents for the first block, the plot on the left-hand side shows that the sample efficiency is almost equivalent for RePReL and ReNN. But as we evaluate the learned agents on different tasks by increasing the number of blocks, we see that the success rate achieved by the RePReL agent is quite significantly higher than the ReNN agent. And finally, what we did here was we evaluated multimodal data. So what we had here was the taxi location, and the grid was coming as an image, and passenger locations were coming as predicates. And we see the same thing. The HD RePReL is the hybrid deep RePReL. So we see hybrid deep RePReL is better able to transfer across number of objects, as well as here the transfer is across task. So in the first plot, we are trying to make a bread and then build a house and things like that. So we see in general, RePReL agent is able to handle multimodal data. It is able to handle varying number of objects. It can generalize to different tasks and can handle multimodal data. Any questions?
Yes, I have a question. Can you just go back a slide? Cool. So I'm just wondering what do you think the advantages of RePReL? Is it mostly the fact that it can do the symbolic planning, or does it have something to do with the fact that its task specific representation was given by a human, and that the human has, like how much of this algorithm is just the human's contribution to it? I guess the question.
That's a very good question, actually. So looking at this example, for this plot, for instance, TRL, the taskable RL agent here, also has a planner. So it's the same symbolic planner at the top and reinforcement learner at the bottom, the same similar framework. What they do is they have a different definition of the options, or the RL MDPs that are defined is a little different. And they do not have state abstraction. They use all like the complete state observation as it is from the environment to learn each of their RL policies. What RePReL does is a separate, as I mentioned, task-specific representations. And we think that it is because of that. So this is kind of an ablation study that you can see the difference between TRL and RePReL here.
So just to be clear, the task-specific, the state abstractions are learned from the D-foci statements given by humans, right?
Yes, I would not use the term learned. I would term reasoned, but
okay.
I know sometimes people use learn instead of reason as well.
So they're kind of explicitly calculated, right?
Yeah.
Okay. But then so the TRL agent also has access to the same predicates that are used in the D-foci statement.
Yes. So all of them have the same, yeah.
Oh, they all have the same.
Yeah.
Okay.
Representation is the same across, like the domain still stays the same.
Okay, because you mentioned there was a slide on the multimodal stuff, right? So
yeah,
but there was an image that they take in images, but
yeah.
So I guess
so here Go ahead.
Oh, I was just saying that like I guess is the state space the image, or do all of these algorithms have the image plus predicates, which are functions over the image as well?
In multimodal data, it is image plus predicates. That is the location of whatever number of passengers there are. Passengers' current location and passengers' destination. But the taxi location is coming from an image. So in multimodal examples, it is image. Okay. Image plus predicates. In the previous examples, it was just a graph. Okay. Each passenger being we can think of each passenger being a different node in a graph, and the node can have multiple features. So every passenger would have pickup location, drop location, and current location.
Yeah, I understand.
Yeah.
So I also have one more question, which is what do you attribute the decrease in performance of the at the beginning over the DQN?
Oh, there was a very interesting paper. It's called capacitive loss, I think. That we see this, we see, interestingly, we see that the decrease only in the neural or the deep RL baselines, not in tabular RL. And there was a paper in Europe which talked about how deep RL agents or deep neural networks have a memory. Because if they are trained on a particular task, the neurons are trained for that, and so they lose the capacity of learning for new domain initially, and then they given enough examples, they again catch up or they start learning again. So so we believe it's that.
Okay.
Yeah.
Second, wrap up.
Sorry?
Wrap up now. People have to leave.
Yeah, we have 4 more minutes. So after the summary.
I'll just
Yeah.
Okay, so to summarize, we provided a framework that combines symbolic planner with RL agents, and we provide a batch learning algorithm. We demonstrated sample efficiency, efficient generalization across number of objects, and hybrid approaches. Most important thing I would like to highlight is the framework is planner agnostic. We don't really care which planner. In our experiments, we have used the forward downward planner. Yes, FD planner, and HTN, hierarchical task network. And it is also agnostic to the RL algorithm that is used. Any RL algorithm that supports batch learning should be able to be incorporated in RePReL framework. And yeah, so as evidently mentioned, that deemphasized statements are right now specified by humans, and we are trying it might not necessarily be the most accurate one for the domain. So we are trying to refine deemphasized statement. That is something that is currently being pursued by Nikhilesh and me. And then we are in the current framework, we assume a downward refinement. That is, given the current task, if we have if we decompose the task into the specific hierarchy, then we assume that the decomposed task can be achieved without changing the hierarchy or without changing the decomposition that was provided by the planner. So that is called downward refinement assumption. So we want to relax that and may have a feedback loop from the RL agent to the planner, so that we can replan, or maybe have a differentiable planner at the top, so that we can even learn to learn an efficient plan, a high level plan as well. Currently, we assume complete observations. We don't assume any uncertainty over states. We assume that the observation are complete. So we want to also allow for partial observability, especially for the robotic arms domains. If we are trying to extend this work for other robotic domains, then we have a vision area. So we want to try and also incorporate partial observability. And current composition of the RL agent that we use is a temporal one. That is, we assume that all the RL agents at the lower level are composed together in a temporal fashion, one after the other. But there's a interesting work which talks about composing RL agents as a Boolean algebra. So we are trying to also extend, we are interested in also using that with RePReL framework. That would be it. Any questions?
I'm fine. I have a question. So when you're designing your foci statements, have you ever considered how you might handle uncertainty in the number of steps between kind of when a influent is activated and when the resulting condition becomes true?
That's a very wild question. We are in a Markov assumption, Markov decision process space. So we assume Markov property.
Any other questions? Okay. Thank you, Harshit.
Thank you.
So there's one-on-one time, there's another slot. I'm speaking to her till 1:30. If any one of you wants to sign up, please do. Yeah. All right. So meet you back again on the same Zoom in like 5 minutes.
All right.
Yeah. And we'll
Okay.
chat one-on-one. Yeah. All right. Thank you.
Alright.
Thanks again.
Thank you,
Bye-bye.
everyone, for your time. And you can reach me on the Twitter if you need.
Yeah.
Thank you.
Cool.
All right. All the best.